Hello and welcome to lesson 2.6, more on least squares regression lines. LSRL stands for least squares regression line, and we learned an awful lot about it in the last video, but there's still an awful lot left to learn here, which is actually pretty cool because least squares regression lines are really powerful. And if we're going to use them to make predictions, we better make sure that we're using the right, appropriate equation and that we can rely on those predictions. So that's what this video is kind of all about. All right, so let's talk about a couple more facts about the least squares regression line. Number one, the distinction between the explanatory and the response variable is essential. You cannot reverse the roles of x and y. Regression lines take an x to predict a y. It does not work the other way around. I did mention this in the other video when we were trying to predict the weight of a baby based on its age. We could take an age and predict its weight, but it cannot work the other way around. We cannot take a weight and work backwards to predict its age. So it does matter who is x and who is y. But I want to emphasize that correlation actually does not care. R all by its lonesome self does not care who is x and who is y. But you better believe that the slope in the equation does. Number two, the slope tells us a lot about the correlation. Remember the formula to calculate slope? If you know all of the data, the correlation or the slope B is R times the standard deviation of y divided by the standard deviation of x. Now this is actually really cool because this is what tells us that if in terms of your x variable, if you move up one standard deviation in x, then you move up r standard deviations in y. So think about that, right? Actually, it makes sense if I treat this r as r over 1. So every time I go up one standard deviation in the x variable, I go up r standard deviations in the y. And of course, if r is negative, then I would be going down r standard deviations in y. So it just shows how these two variables are connected and why correlation really matters. So if you go up one standard deviation for x, you go up r standard deviations for y. And this is actually really cool because this is where we get the term regression equation. Maybe you've been wondering the whole time, why do we call it a regression line? The definition of regress is to move backwards, to fall behind. And this actually makes sense. Here's why. In terms of x, if I go up one standard deviation, right? One standard deviation. Now, y can only go up r standard deviations. And I say only because remember, r is never going to ever be 1. R being 1 would be a perfect relationship. X goes up 1, y goes up 1. That's a perfect relationship, and you don't really ever see that in a true scatter plot. So r is always going to be a little bit less than 1. Like, let's say r is 0.92. I mean, that's still a pretty good r value, but it's still less than 1, which means as x goes up 1 standard deviation, here comes y, he only goes up 0.92 standard deviations. So y is always falling behind x. He's always regressing behind x. X goes up 2 standard deviations. Y can only go up 2 r standard deviations. So again, he's always regressing behind, and that's where we get that term regression line from. So hopefully that makes sense, but it's pretty cool that that is how the formula for slope works. All right, more facts. The least squares regression line always passes through the point x bar, y bar. Remember that the formula to find the y-intercept, whether you call it a or b sub 0, the formula is the average y minus the slope times the average x. And because you use the average x and the average y to build that equation, to build the y-intercept, your line naturally will go through the average x comma the average y point. Kind of neat. All right, now there's this next idea we're going to talk about is r squared. Now we all know what r is, right? R measures the strength and the direction of a linear relationship between two quantitative variables. But if I take r and simply square it, I get something very, very different. It's called r squared. It's also known as the coefficient of determination. Now I'm going to talk a little bit later in this video about the importance of r squared, but r squared is really, 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 really important. So, how do we interpret it? First off, r squared is made into a percentage. So let's just say that r squared is 0.814. Then we would interpret that as 81.4%. And what r squared does is it tells us the percent of variation in the y that is actually due to the variation in the x. Remember, you have to understand that our line is not perfect. Our points are always varying from the line. Some are a little bit higher, some are a little bit lower. So when we use our least squares regression line, there's always a little bit of variation, right? We're not perfect. X does not direct correlate directly with y. There's a little bit of variation there, which is why we don't ever really have a correlation of exactly 1. So r squared actually puts a percentage on how much of that variation for the y variable is actually due to the variation in the x variable. Now, there are 3 ways to interpret r squared. Here's the first one, here's the second one, here's the third one. I'm actually going to recommend the third one, but all of them are correct. So 1 is it's the percent of variation in the y that is due to the variation in the x. 2, it's the percentage of variation in the y that is explained by the variation in the x, just using a different word there, explained versus due, same thing. But the last one that I actually like, that I think makes a little bit more sense, is it's the percentage of variation in the y that is accounted for by the least squares regression line. You have to understand that when we build this line, we account for the idea that there is some variation, right? Not every point perfectly fits the line. So r squared actually puts a percent value to what percent of the variation is actually because of your line. And we're going to talk a little bit more about this in a couple more slides, but this is a really important value that tells us how reliable our line is. Basically what we're saying is that if you have 2 variables x and y and they have an 81.4% r squared, that means that 81.4% of the variation in that y variable is actually due to the least squares regression line, which is really, really powerful. It tells us that there's a strong connection between these 2 variables and that it's reliable. We'll talk a little bit more about that in a more specific example in a moment. All right, let's go back to residuals for a second. How do the residuals behave is very important in assessing how well our line fits the original data. Just think about it. We want a line to go through the points. And if your line goes through your points but has a whole bunch of really big residuals, then I don't know if we have the best line, because we want those small residuals. We want the actual line to go through our data, not around it, through it. So the residuals should be all mixed up, meaning some should have high ones, some should have low ones, and in no particular order, right? So we should see some positive and some negative residuals, and in no particular order. Also, the sum of the residuals should be 0 because of the fact that some points are below the line and some points are above the line. Let me explain this a little bit better with some examples here. So here's a bunch of blue dots, right? They make a scatter plot, and there's my red line of best fit, which we call the regression line, the least squares regression line. Now, notice how my line goes through the dots. That's a good line. That shows that my line represents those dots very, very well. Now, look at this data. The blue dots clearly form a curve. And if I try to use a straight red line to go through it, it doesn't really go through it. The residuals are positive here in the beginning, and then they're all negative in the middle, and then at the end they're back to being positive. So this is actually a sign that my residuals are not mixed up. There's kind of like a pattern there, like positive residuals, then all negatives, then all positive. Let me go back to this one, which was excellent. Notice that in the beginning of my data, I had positive and negative residuals. I had points above and below the line. In the middle, I had positive and negative residuals. And even at the end, I had some positives and some negative residuals. That means that my red line was going through the data the entire time. When your data has a curve to it and you attempt to put a straight line through it, now why you would even do this I don't know, but if you attempt to, you notice that the residuals don't become mixed up. They're all positive in the beginning, then all negative, and then back to all positive. Here's another example that makes it really, really clear. Once again, I clearly see a parabola forming with my blue scatter plot. And if I attempted to put a straight regression line through that data, that would be very dumb. But the residuals inform me of how dumb this is. Because the residuals say, dude, listen, you're not going through our data. You have all positive residuals, starting big, getting small. Then you have a whole bunch of negative residuals, starting small, getting big, starting and then going back to small. Then you have a bunch of positive residuals again. The point is that my line does not go through my data. We want it to go through the data, like this very first one. These curved ones, the line doesn't go through the data. And the residuals tell me that. The residuals are informing me that because there's this pattern to the residuals, positive, then negative, then positive, same thing here, that's telling me that, you know what, hey dude, a line is probably not the best model for your data, which obviously I see that. I should have known that from the beginning, but it actually proves a point that residuals really help confirm that for us. So a residual plot is a way that we can more closely examine the residuals. Okay, now residual plot is a scatter plot of the x values versus the residual values. So instead of looking at x versus y, that's a scatter plot, a residual plot looks at the x values versus the residual values. And when we look at a residual plot, we want to see absolutely nothing. The residuals should be all mixed up, positive and negative, large and small. This proves that the line goes through the points. So a residual plot that shows no pattern is an indicator that a linear model is appropriate for the data. Here's an example of a residual plot. So notice that first off, the scatter plot goes positives and negatives. And that makes sense because residuals are positive and negatives. So right smack dab in the middle is 0. That would be a residual of 0. Now, if all of our points had a residual of 0, that would mean that every point fell on the line, a perfect fit. Now, obviously, that's never going to happen, but a line of 0 in the center here is like my perfect line. If you are on the regression line, you have a residual of 0. And we should see positive residuals, meaning dots that have positive residuals that would be above the line. We should see negative residuals, that would be dots that are below the line, and they should be mixed up throughout the entire thing. So in the beginning, whoops, sorry about that. In the beginning, we should see positive and negatives. In the middle, we should see positive and negatives. And at the end, we should see positive and negatives. That shows that my line really does go through my data and that a linear model is appropriate. So when it comes to determining is a linear model, a least squares regression line, an appropriate model for your data, we really want to make sure that we check the scatter plot, right? Make sure your scatter plot is somewhat straight. If your scatter plot has a giant curve in it, you should never be using a line anyway. But we also now want to add this residual plot to that. We should be checking the residual plot that shows no pattern. So I believe I want to show you how we could actually do this on your calculator. And if you just want to follow along with me, that's great. If you really want to enter the data in, you can. Now, in that previous video, when we did the last lesson, we looked at baby weights and their age. So I actually went and entered all the baby weights into my calculator. So I entered all of their ages and as the x variable. And there they all are for all of the 16 babies. And then I entered all of their weights in. There they all are for all of these 16 babies. Now, let's just run through a real quick everything you could do with this. First thing I'm going to do is I'm going to take a look at the scatter plot, right? So I'm going to look at list 1 versus list 2. List 1 was my ages. List 2 was my weights. Make sure you have the scatter plot chosen. And then don't forget to quit. Sometimes you just got to quit out of there first. And then zoom number 9. There's my nice scatter plot. Yay, looks straight, looks awesome, right? All right, now the calculator can actually make residual plots for us. It's really cool. Now watch this. Get ready for this. This is my favorite thing that I like showing. You probably won't get as much excited as I am here. But let's actually run a linear regression real quick. So we're going to go stat calc, and then we're going to go down to number 8, remember, linear regression, a plus bx, okay? And then we're going to tell it list 1 is the x's, list 2 is the y's, make sure all that is correct, and then we're going to hit calculate. Now this gives us the equation. If you remember from that video, these were the y-intercept was 9.8278 and the slope was 0.9735. And r squared was 0.9429, r was 0.97. This is all great. Now, the moment you run this linear regression, the moment I hit enter and this linear regression pops up on my screen, the calculator, without you even knowing it, automatically calculates the residual for every single one of your points, and it stores them into a list called residual. Now, to access that list, you have to hit second stat. Right above stat is list. This is think of this as a list of your lists. It's a list of all the lists. And at the very bottom, for me it's at number 7, but for you it could be even lower. You just got to find it. But at the very bottom is a list that should be named resid. This is literally a list of your residuals. And as long as the last thing you did on your calculator was run a linear regression, the residual list would be a list of all those residuals. So there should be 16 residuals here. So you should see that some of them are negative, some of them are small, some of them are big. There's a positive residual there. There's a 1.4. It's kind of a bigger residual, but positive. There's a small positive residual. The cool thing is the calculator makes all those residuals for you. Then to take a look at a residual plot, you hit second y equals, go back to your plot 1, and instead of looking at the the age versus the weight. So let's look at age versus residuals. So I'm going to go leave the X list as list 1, but instead of looking at the Y's for list 2, we're going to hit second stat, which is again the list of lists, and we're going to go and grab that residual list. So we're literally going to look at our ages versus our residuals. Now once this is done, you got to remember that you have to re-hit zoom 9. And here is a residual plot. And this is another good residual plot because on the left I see positive and negative residuals, some big, some small. In the middle I see some positive and some negative residuals, and even at the end I see some positive and some negative residuals. So I don't see any clear pattern. What we don't want to see in a residual plot is a giant clear curve. Now in this residual plot, it doesn't look, there's not literally scatter everywhere, but at the same time, I don't see any major pattern. I see literally a bunch of dots kind of scattered everywhere. That's what you want to see in a residual plot. That is a line that is, proof that our line went actually through our data, and hopefully that makes sense. So your scatter plot needs to look straight, and your residual plot should show no pattern. All right, the next question I want to answer is how can you tell if a linear model is reliable? So in the last one we looked at if it's appropriate. Now we want to look if it's reliable. So if I'm actually going to use this least squares regression line, I want to make sure it's worthwhile. So now there's two things that we look at here to make sure a line is reliable. The first is the coefficient of determination, which is called R squared, which we talked about already, but we're going to talk about again. And the second thing we want to do is examine S. S is the standard deviation of the residuals, and we'll talk about that in one moment. So let's talk about the coefficient of determination. Now, I'm not going to lie to you. The coefficient of determination, which is R squared, is a little bit weird to understand. Some kids never truly understand it. They just kind of remember what to write down about it. And I'm going to do my best to make sure you understand this, but it can be a little bit tricky. So first off, I have two lines here. Notice that the red line is my actual regression line, right? The line that goes through the dots. This, by the way, was our age and weights of the babies again. Now, the green line is simply the average Y. And what we do is we say, okay, clearly the red line is better, right? Because the square residuals are all the smalls. If I look at the square residuals for every one of these dots, right? Here is the square residual. It's kind of a big square. Here's going to be a small square, and there's going to be some small squares. If I look at all of the square residuals, and most of them, because this is such a good line, most of them are pretty small, which is exactly what we want, right? We want small square residuals. That way when we add them all together, we get really, really small square residuals. Now, if I use the average Y, like if I just said, hey, you know what, for every baby, no matter how old you are, I'm just going to guess the average weight. So I don't care if you're young, I don't care if you're old, I don't care if you're 2 months, 4 months, 6 months, 8 months, or 18 months, I'm just going to guess the average. 17.6, that's the average I'm going to guess, which would obviously be stupid to guess the same number for every baby no matter their age, but that's what the green line would be. Now, if I were to calculate the square residuals for that, they would all be huge, right? Look at how big these square residuals are. Now there's some small ones in the middle where it is kind of close, but on the ends they're huge. The idea is that if I compare the sum of the square residuals for the actual best regression line and just using the average Y for all my guesses, we start to understand how much variance there is, right? We start to understand that there is, most of the dots are going to be near the red line because that's why we chose that red line, right? And then the green line is not really good at making predictions. But if we look at the proportion of variance between the red line, which is clearly better, and the green line, what we get is we get a percentage of data that shows us that things are unaccounted for, right? Some of the variation is unaccounted for. Meaning, to put that in context, if you think about the weight of a baby, age has a lot to do with it, and that's what correlation tells us, right? So if we were to find the coefficient of determination and we square it, right? Which, if we actually go back to our computer, or our calculator, which I guess is a computer, we did this a moment ago, and it actually tells us that R squared was 0.9429, right? That tells me that 94.29% of the variation in a baby's weight is actually accounted for by my line. So us seeing these varying weights of a child is actually due to the variation in their age. Right? That actually makes a lot of sense. That tells me that this line is very reliable. You know, I'm not trying to simplify this too much, but I want you to understand it because it can be a little bit confusing. But what I'm trying to say to you is that 94% of the variation in a baby's weight is actually because of the variation in that baby's age. Think about that for a second. I'm actually connecting these two variables, and I'm telling you that they are very strongly connected. Now, are there other things that determine a baby's weight? Yes, genetics. Some babies are just bigger or smaller than others because of genetics. How much they eat, right? Their parents' size. There's a whole lot of different things that determine the actual weight of a baby. But what I'm trying to say here is that age is accounting for a lot of that. 94% of the variation in a baby's weight is actually accounted for by that baby's age. And that makes a ton of sense. The other 6 or 5 some odd percent could be due to those other things, but a large chunk of it is due to a baby's age. And that's really, really important. That's why coefficient determination makes a lot of sense. Because if I were to just use the mean and guess every baby's weight, I'm just going to guess the mean of all babies, I'm not going to be very accurate. Maybe in the middle I will be, but on the ends I'm not. And that's what we're trying to make as. That's why our red line is very, very reliable, because it's better at making those predictions. And why is it better? Because 94% of the variation in weight is actually explained by the least squares regression line. All right, let's talk about S, the standard deviation of the residuals. This is basically the standard deviation of all the residual values. So if you think about that, we have all of our residuals, and if we think about how far is a typical residual, right? How far is a typical point from the line? That's kind of what we're doing here, right? When we use the regression line to make a prediction for Y, we are typically going to be off a bit. The standard deviation of the residuals tells us how far off we typically are when making those predictions. You have to understand that anytime you use a regression line to predict something, you're not going to be perfect. You're going to be off a little bit. And wouldn't it be great to know how much we're typically off? That's what S is. Now, look at the formula for S. It's a little bit confusing. It is taking the sum of the square residuals. So Y minus Y hat is a residual for each individual Y. So I take each individual Y's residual. So I take every point's residual, square them all, then add them together, divide by n minus 2, and then square root it. Honestly, don't worry about remembering this formula. You're never going to use this formula. You're just going to be given S. But you need to know what S measures. Again, it measures how far away typical data is from the regression line. And it's a really cool value. And a lot of kids don't ever really understand it. So if you take the time to actually pause and read this slide, I think it'll make a lot of sense to you. The standard deviation of the residuals tells us how far off we typically are when making a prediction. And we want to be off by a small value. We don't want to be off by a large value. All right, here's one last kind of look at this baby problem that I hope can really kind of make all of this kind of, make sense to you. So first off, the question I could ask you is a line appropriate for this data? Two things. One, the scatter plot looks straight. That's a good thing. Two, if you recall earlier in this video, we looked at the residual plot. The residual plot should show no pattern, meaning positive and negative residuals throughout the entire thing. That's a good line. It shows that your line is going through the data well. Now, is this line reliable? Well, that's going to come down to R squared. If you literally take R, 0.9710, and square it, you get 0.9429. In R squared, we do make a percentage. We never do this with R. Please don't ever make R a percentage. It's only R squared. So we know that 94.29% of the variation in a baby's weight is actually explained by the least squares regression line. So 94.29% of the variation in a baby's weight. Oh boy, my writing is just becoming atrocious here. I really do apologize. I'm going to restart that. In a baby's weight is accounted for by the least squares regression line. And that is very, very powerful. And I hope you truly understand that. But like I said, most kids just remember what to write down, unfortunately. All right, now the last thing is the S value. The S is 1.1158. Now the S value is the how far a typical prediction is from the regression line. So this is going to be measured in our same unit for Y, which is going to be pounds, right? We were measuring these babies in pounds. So this tells me, and this is like so important, this should if anything makes sense in this video, this should. When I use this red line to predict the weight of a baby, I'm typically off by 1.12 pounds, 1.1158 pounds if I want to use some more decimals. That is really powerful. That means that if I'm going to guess a baby's weight simply based on this regression line, I'm going to be off. How much am I going to be off by? About 1.12 pounds. Above or below, I'm going to be off by 1.12 pounds. Now, you have to make the decision, is that a big or is that a lot? Well, if you're trying to predict a baby's weight and you're only off by 1.12 pounds, that's really not too bad. Obviously, I'd prefer a very small S value. Well, duh, that makes sense. I'd prefer to have a very, very, very small value. Like, I'd prefer to only be off by 0.1 pounds, but it is what it is. Smaller is obviously better. Obviously, if I was off by 20 pounds, if you're trying to predict a baby's weight and you're off by 20 pounds, boy, that's not a very good prediction. So I think 1.12 pounds is pretty standard. But make sure you understand the interpretation of that. It's when we use this line to make a prediction for a baby's weight, we're typically off by 1.12 pounds. Pretty straightforward. Now, you also got to think about what you're doing, right? If you're trying to predict the weight of a mouse and you're off by 1.12 pounds, boy, oh boy, I think you're doing pretty poor because mouse don't weigh very much, mice don't weigh very much at all, and if you're off by 1.12 pounds, you are way off. But if you're trying to predict the weight of an elephant and you're off by 1.12 pounds, holy cow, that is very accurate. So again, you have to not only think about big versus small when you're working with S, but you also think about the context of the problem. Is that number telling me that I'm very reliable or not very reliable? So that is it for the reliability, right? We look at R squared and we look at S, and I hope that those two values make a lot of sense to you. All right, next up here, we're going to look at influential points. All right, influential points are often outliers in the X direction. Influential points have low residuals because of the fact that they are so influential, they pull the regression line towards them. Sorry for the typo there, line. But influential points also affect the slope in a big way. Now you might be like, okay, what's an influential point? L-I-N-E for line there. All right, influential points most kids are just going to call outliers, right? They're points that don't seem to fit the pattern. But not all points are equally outliers, right? I want to talk about a true influential point, and I'm going to talk about these three facts here. One, they're typically outliers in the X direction, and they typically have low residuals because they affect the slope in a major way. So let's look at a couple different outliers in terms of scatter plots, and we've actually already done this in a couple of videos ago, but I'm going to emphasize it again to really talk about influential point. So let's look at this outlier. This point right here is an outlier only in the Y direction. I'm going to be honest, a point like this does not affect your slope very much. Here is my line of my regression line. Sorry, that's not very straight, but you get it. It goes through the points, right? If I were to get rid of this point that's an outline in the Y direction, that line's not going to change a whole lot. It really isn't. Now, it might change a little bit. Obviously, if you take away that point, your correlation is going to get better because that point doesn't fit the pattern. But, I mean, the line's not going to change a whole lot because it's in terms of X's, it's right in the middle of everybody else. So the addition or the subtraction of this type of point is not going to affect your slope. It's definitely an outlier, but it's not what we call an influential point. All right, here is a point that's an outlier in both the X and the Y direction. Will this point affect your slope? Absolutely not. Here is my line without that point. Here is that line with the point. Did the slope change? No, my line extended, but the slope didn't change at all. So again, outliers in both directions, X and Y, are not influential points either. This is an influential point. This guy down here is an outlier in the X direction, not necessarily the Y. Now he is a little bit low for his Y, but it's not like he's this big Y outlier. Now, here's my slope, here's my line, without that point. With that point, my line is going to make a major change like that. Now I'm going to be honest, I made this very, very dramatic to show you this, but the point is, if you are an outlier in the X direction only, you are influential. You're going to really pull that slope. We call it leverage, right? This type of point has a lot of leverage to pull the line towards it. Now, my example might have been a little dramatic there, so I'm going to give you one. This might be a better example of an influential point, okay? Meaning that it's clearly not an outlier in the Y direction. In terms of Y's, he's actually right smack dab in the middle of everybody else. But in X's, he is definitely a little bit more to the right than everybody else. But a point like this is going to pull the line towards it because it has leverage, right? It's like, leverage, if you think about physics, right? If you have a teeter-totter and you push down in the middle, you don't have a lot of leverage to change that teeter-totter. But if you push down on the end, you have a lot of leverage to move that teeter-totter down. It's the same idea here. Points that are outliers up here in the Y direction, they just don't have a lot of leverage to change your slope. But points that are outliers in the X direction, they have the leverage to really influence your slope and change it. So you'll notice that here was my slope or my equation. Here's my line without that blue point, but then with that blue point, my line has to make a major bend, a major slant to adjust for that point.